this video we're going to learn about the alternating current through a resistance and many more. I told you in the last video that the most important topics in this chapter are resistance through a resistive circuit, capacitive circuit, inductive circuit. We need to calculate the resistance. Actually, we are dealing about the alternating current through all of these and then these combinations. So first of all, we have the resistive circuit. Though these three questions are not that important, usually it's not asked in the examination. Still, it's important to understand these things before we move on to the other combinations. So first of all, we have the alternating current through a resistance only. So it is a case of purely resistive circuit. So first of all, we'll draw the circuit diagram. If it is the case of purely resistive circuit, we'll only have a resistor, and obviously there will be a source for the alternating current. We denote it this way. So this is an AC source, and this is a resistor. So this is a resistor of resistance R. The resistance of this resistor is R, and we know that the source, AC source, it will provide some potential difference, which we usually denote by V, but in case of this AC circuit we denote it by E. This is the EMF. Now let me tell you some information about the EMF and voltage. Basically, we know that if there is a normal circuit, positive terminal, negative terminal of a battery, and what happens is that this is the positive, this is the negative terminal. We know that the current is flowing from positive to negative, but actually the electrons are flowing from negative to positive. So the electrons flow from negative to positive, and basically current is the flow of electrons, and it is in opposite direction of the flow of electrons. So if the electron is flowing from negative to positive, the current is from positive to negative. So basically the work which is done to move this unit electron, unit charge, one electron, that is known as EMF. And if you remember, this is the definition of the potential difference as well. Potential difference is basically the work done in moving the unit charge. Unit charge means one electron, and that's what EMF is. So the difference is that in case of DC circuit we denote it by V, and in AC circuit we denote it by E. So V and E are basically the same thing, only the denotations are different. So coming back to the topic, this is the circuit which is only containing of a resistor. So this is a purely resistive circuit and an AC source. So this AC source will provide some potential difference. We will denote it by E. So this AC source is providing a potential difference E, and we know that E equal to E naught sine omega t. So this is the potential difference which is applied by the AC circuit. So now remember, if it is the question of only purely resistive, purely conductive, purely capacitive or purely inductive, only it is the case of purely, it means either it is containing only resistor, only inductor, only capacitor. We always begin from E and then we go to I. So basically what we are doing in this chapter is, in this topic is, we are comparing E and I. Which one is forward, which one is more ahead, either E is ahead or I is ahead. So we begin from E in case of single combinations, and if there are cases in which two or more than two combinations are there, for example like resistor and capacitor, or inductor and capacitor, or all the three, resistor, capacitor and inductor, we begin from I and then we go to E. So in case of combinations, I to E, and in case of singles we go for E to I. So we begin from E. So we know that the alternating EMF which is applied to the circuit is E equal to E naught sine omega t. This is the EMF which is applied to the circuit by the AC source. We also have the formula V equal to IR. Now for AC it will become E equal to IR. We know this E and V will be changed for an AC, V equal to E. So basically the PD across the resistance, the potential difference across the resistance, it will be V equal to IR. It means E equal to IR. So we know E equal to E naught sine omega t. E naught sine omega t equal to IR. And then we see that we are going on for the I, so we'll isolate the I. So I will come one side, and E naught sine omega t upon R. And see, E naught upon R is I naught. So I equal to I naught sine omega t. Now I'll clear all these things once again. From the beginning, see, we know that the alternating EMF which is applied to the circuit by the AC source is E equal to E naught sine omega t. and the potential difference which this resistor is receiving, it is V equal to IR. It means E equal to IR, anything. So this is the resistor, this is the potential difference which is across the resistance. So E equal to IR and E equal to E naught sin omega t. So E naught sin omega t equal to IR, and we are going for I, so we just isolate the I here. I equal to I naught sin omega t by R. Now see, E naught by R, it is basically I naught. Now in this whole chapter we're going to use this formula V equal to IR everywhere, okay? So we know V equal to IR. For AC we use E equal to IR. So I equal to E by R, and if it is the case of E naught, then it will be I naught equal to E naught by R. In this way, this E naught by R becomes I naught. So now you got how E naught by R became I naught. It is basically the same thing, V equal to IR, so I equal to V by R. In case of AC, it is E by R, and since there is naught here, even in I there will be naught. So in this way, I equal to I naught sin omega t. So finally we are seeing that this I naught, which is equal to E naught by R, this I naught which is equal to E naught by R, this is the peak value of the AC. So finally we are seeing that this E equal to E naught sin omega t and I equal to I naught sin omega t, both are in the same phase, because see, the angles omega t and omega t are same. There is no plus 90 degree or minus 90 degree. Since they both are in the same phase, so none of them is ahead. They both are moving with the same phase difference. Now after this, though this question is not asked, but if it is asked, we need to draw the phasor diagram, and then we need to draw the variation of the alternating EMF and alternating current in a graphical form. Now this phasor diagram, if we understand right now, it will be beneficial for the topics. So now let's begin from the phasor diagram. In the writing part, you just need to show only this much, this part. It's very short. So now basically how we draw the phasor diagram. First of all, we draw the four quadrants. It's X dash Y, Y dash, and this is 0. So now remember, first of all we draw the thing from which we are beginning. Here we are beginning from E, so we draw an arrow. You draw the arrow in the first quadrant, okay? So we draw the arrow in the first quadrant and we are beginning from E, okay? So this is E and this is E naught. E naught means the peak value, and even I naught means the peak value. So this peak value is E naught and this is E. So basically we just write A naught. There's no necessity to write the E. So this is E naught, and we know that they both are in the same phase from the derivation part. We see there is no phase difference. Both are in the same phase. So what we do is we draw the I over this, but slightly smaller. Now you need to understand that everywhere in the phasor diagram you need to understand this thing, that always E naught, it will be bigger than the I naught. So this EMF will be bigger than I. So this is a thing to remember, that always E naught, it will be bigger than the I naught. So this is I naught, this is E naught, and basically this angle is omega t. The thing we are writing sine omega t, so this is omega t, the angle, and this is all about the phasor diagram for this purely resistive circuit. Because they are in the same phase, so we are not drawing I naught here or here, we are drawing overlapping it. So now this is about the phasor diagram. What about the graphical representation? So for the graph we do this, actually that is the waveforms. So we draw here time, and this is the part which represents E or I. So now we begin from E here, because we are beginning from E, so we start from the E. It means EMF. So you need to remember, divide this into 6 sections, okay? So after dividing them into 6 sections, you need to name them. This is pi by 2 and this is pi. Now after this, it is 3 pi by 2, and then this is 2 pi. Now this is 5 pi by 2, we are just increasing it, and this is 3 pi. So if you do not get how to write it, there is a trick for that. See, pi, 2 pi and 3 pi, we got that. And here see, pi by 2, just add 3 there and then add a 5 there. So that's just a simple trick, but basically you can remember this, it's very easy. Pi by 2, and then we have pi, and then 3 pi by 2, we have 2 pi. We are just increasing by pi by 2. We are increasing every section by pi by 2. So now we begin from E, as I said. So just simply draw any of anywhere, okay? It's not necessary that you need to draw the peak value here or here. It's not that. You can draw anywhere. So just draw E first of all randomly as you want. But you know, again, this and this should be same, okay? The peak value is constant. So this is a simple figure of E. So we know this is E, and this is the maximum value, which is the E0. Even this is the maximum value, which is the E0, though in opposite direction. Now we know that the I, it is basically in the same phase as of E. It means current is in the same phase of EMF. We got the conclusion from this part. So we do not draw E ahead or behind, we draw from the same phase. But as we know that E is always smaller than I is always smaller than E, so we draw from here because they are in the same phase. We are drawing from this part. If it would be ahead, we would draw from somewhere else. I'll tell you in the next part. So right now we are drawing this E, which is smaller than the I. So we are drawing smaller than this. See, it will be smaller than E. This I is smaller than E. Always you draw it smaller. So this is I0, which is the peak value, and this is basically I. So that's all we need to draw in the waveform, and that's all we need to draw in the purely resistive circuit. Hope you understood this. If you didn't understand, I'll tell you, just summarizing it once again from the beginning. First of all, see, what we do is we begin from E equal to E0 sin omega t. Now what is the potential difference which is being applied in the resistance? It is V equal to IR. For AC we write E equal to IR. We know E equal to E0 sin omega t, so E0 sin omega t equal to IR. Now we are calculating I, so we just isolate the I, and E0 sin omega t by R, and E0 by R is I0. So I equal to I0 sin omega t. From this we conclude that both of them are in the same phase. Since they are in same phase, we do not draw ahead or behind this, we draw overlapping it, but I is always smaller than E, so we drew it smaller. In the waveform, what we did is, first of all, we randomly drew the EMF. Okay, we randomly drew the EMF, and then we drew the alternating current, which is slightly smaller than it, but beginning from the same point, because they are in the same phase, so they are beginning from the same point. So that's all about the purely resistive circuit. So now we have the alternating current through an inductance only. It means purely inductive circuit. Now remember, this is not hard, this is not difficult, but this is quite complex and confusing, so you need to pay attention, pay full attention actually here. So first of all, if you just go for it looking for in the book, you'll find it quite confusing and complex because the things are in such way. But you need to practice this twice or thrice, and then you'll be perfect in this. And remember, though this question is not asked in the examination regularly, but it is very important to understand this part for combinations. So first of all, we begin from the same thing. We draw the circuit diagram. If there is only inductance, then we only draw the inductor. Now this is the symbol for inductor, okay? And we will have an AC source. So this is our AC source, and this is the inductance or inductor. So now as we begin in the last part, E equal to E0 sin omega t. Now here, like in the resistance, the induced EMF which was in the resistance, it was given by Ohm's law. We simply used the Ohm's law, V equal to IR, it means E equal to IR, and we calculated the induced EMF there. It means we calculated the current there. So in this is the case of inductance, it is not the case of resistance. So we cannot apply Ohm's law here, V equal to IR and E equal to IR, and then we cannot calculate I simply. Here different things happen. So what is the induced EMF in this inductance? In this inductor, the induced EMF, it is given by a formula which is equal to L di by dt. Now basically this is the formula you must have read in the Lenz law, and I have even made a video on this. If you have forgotten this, you can go to my video. I have provided the link in the description. So this is the formula for induced EMF, where L means the coefficient of self-inductance. It means, if I'll tell you some of the video right now. Here, for further, you can just go to that video and understand. We know that induced EMF E is given by minus d phi by dt. Okay, it is basically the magnetic flux. It means this induced EMF, it is basically the rate of change of flux. So this is flux and this is time, rate of change of flux. We know E equal to minus d phi by dt and phi equal to Li. Because I is directly proportional to phi, it means current is directly proportional to the rate of change of flux. So so phi is directly proportional to I and phi equal to Li, where L means the constant. So in this way, phi equal to Li, it means dLi by dt, and this is minus, and in this way finally we get minus L di by dt. The complete information is in my video, you can go back to that. So right now we just need to understand that this is the formula for the induced EMF in this inductor. So basically the induced EMF E is given by L di by dt. We do not use minus because in derivations and numericals we do not use minus. It is just representing that the induced EMF, it is of opposing nature, so we do not use the minus sign here. So now E equal to L di by dt. In the resistor we used E equal to IR and then we calculated I, but here we are using I L di by dt and then we'll calculate I. So we are calculating I, so we need to isolate the I. First of all, E equal to E naught sin omega t. So E naught sin omega t equal to L di by dt. Now we are calculating I, so just isolate. So di will be E naught sin omega t into dt. So it will be dt upon L. So now this is the di, we got di, but we need the I, complete I. So what we do is we just integrate di to get I. So we are integrating the di to get I. So the integration, we just write what we have got. E naught sin omega t dt by L, E naught sin omega t by dt by L. So now the integration of di is I. Now here constant terms will come outside. E naught and L are constant terms. So sin E naught is maximum value and maximum value is always constant, and L is obviously a constant, as I said you. So sin omega t dt remains inside, and the integration for sin omega t dt, we have the formula. It is minus cos omega t by omega, because two angles are there, omega and t, and as per the formula the first angle will be in the denominator. So the formula is minus cos omega t by omega. So I equals to this omega will come here, and minus is also there, cos omega t. So right now we got this value for I, but we need the value in terms of sine. Why do we need in terms of sine? Because we are comparing E and I, and for comparison it should be sine omega. Since it is sine omega t here, it should be sine omega t or sine omega t plus something, anything, but in terms of sine. So we need to convert this cos in terms of sine. Now what is the formula to convert this cos in terms of sine? So you need to understand one thing, that you need to understand about the Cos Rule before we go ahead here, because we need to convert this cos in terms of sine, and we convert using the Cos Rule. So I'll just tell you one thing. First of all, let's do it. It will be E naught L omega, and it will be sine omega t minus pi by 2. Sine omega t minus pi by sine omega t minus pi by 2 means cos omega t. Now how actually sine omega t minus pi by 2 is cos omega t, and how did we come to know that? We need to understand it by using the Cos Rule. This is just a rule, a trick to understand this. So see, first of all, there are 4 quadrants. Okay, so the first quadrant is this, second, third and fourth quadrant. You need to remember the cast rule means CAST. We begin from the fourth quadrant. This is not about this thing, this is completely out of course. I'm just telling you so that you can have the ease to understand this. So CAST, it means cast rule. Now we write C in the fourth quadrant. So see, C means cos and sec. A means all positive. It means in A all the trigonometric ratios will be positive. S means sine and cosec, and similarly tan, this T means tan and cot. So basically CAST means in this fourth quadrant cos and sec will be positive. Here all the ratios will be positive. Here sine and cosec will be positive, and here tan and cot will be positive. Now how it will be positive and what does this actually mean, I'm going to tell you this now. So suppose we are given something like this, sine theta plus 90 degree. So we need to know what is sine theta plus 90 degree or sine 90 degree plus theta. So how do we come to know what is the value of sine 90 degree plus theta? So see, here is the trick. We know this is first of all 0 degree, isn't it? And then it goes here till 90 degree. It goes like this, 90 degree, and then again more 90 degree. It means 90, and here it will become 180 degree, and then again it will go more 90 degree. It means here it will become 270 degree, and finally more 90 degree to become 360 degree. So in this way, from here to here it is 90, here to here it is 90 to 180, 180 to 270, 270 to 360. So now sine 90 plus theta means we need to understand that 90 plus theta, this is the 90 plus theta, it means it will fall in this quadrant, and sine 90 plus theta, and it is falling in this quadrant. In this quadrant sine and cosec are positive, so obviously the value will be in positive terms, and the answer will be cos theta, yeah. And now you need to remember that in 90, if it is given 90 and if it is given 270, sine will turn into cos, tan will turn into cot, cos will turn into cosec. But if it is given 180 and 360, then it will not change. Suppose here it had been sine 180 plus theta, then what would be the value? First of all, see, you need to see in which quadrant it falls. 180 is this plus theta, so 180 plus theta, it means in this quadrant, and in this quadrant tan and cot are positive, not sine and cos. Sine is not positive here, only tan and cot are positive, so the answer will be in minus. And in 180 there is no change, sine will remain sine will not change into cos, so it will be sine theta. So sine 180 plus theta is minus sine theta. In this way we come to know all the values. You can take any value. For instance, you can take like what is the value of tan 360 minus theta, for example. So now how we calculate this? 360 minus 3, first of all 360, so it will obviously remain tan, because in 180 and 360 the ratios do not change, so tan will not change into cot, tan will remain tan. So we know tan will remain tan, and it will remain theta, but now it is positive or negative, we need to see this thing. So tan 360 minus theta, we know this is 360 also, so 360 minus theta means it is not going up, it is going down, because it is minus. So minus theta means in this, and in this quadrant cos and sec are positive, not tan, so it will be minus tan theta. So in this way you can calculate any of the values, and this is known as the cast rule. It is very important for optional mathematics. You must have read this rule, but I have given you the trick now. Now this was about the cast rule, it was not in our course, but now coming back to the topic, how this cos omega t means sin omega t minus pi by 2. Let us start from a fresh page. First of all, what we did from the beginning, let's not get confused. So see, we know that we begin from E equal to E naught sin omega t. So we know that E equal to E naught sin omega t, but for an inductor we have E equal to L di by dt. I told you the reason once again. So we know E equal to E naught sin omega t, E naught sin omega t equal to L di by dt. From here we calculate di, because we are finally calculating what is the value of I. Is E ahead or I ahead? So we got di. Now what we do to get I, di is there to get I, obviously we'll integrate it. So we integrated it, and after integration we got till here. Okay, we converted sine into cos by using the formula. Till here we got the value. Now after this, what we are doing, how this sine omega t minus pi by 2 came, and why we are converting. First of all, we know that we are comparing the E and I, so for comparison there must be in somewhat same terms. So for similar terms we need the value to be in form of sine omega t plus 90 degree or minus 90 degree. It is ahead or behind. Now remember, not 90 degree plus omega t, 90 degree minus omega t plus 90 degree or omega t minus 90 degree. We are because we are comparing them, and according to the formula you can see that first of all we are using 180 degree plus theta, 360 degree minus theta, but we need theta ahead. I'm telling you this because we are gonna need this now. So let's start from fresh page. Once again, this I equal to minus E naught by L omega. We have minus cos omega t, cos omega t minus is there. So now we need to convert cos in terms of sine using the Cos rule. So till here it will be the same. So see, for conversion of cos into sine, we'll use the Cos rule, and we know according to the Cos rule, sine 90 degree minus theta will be equal to cos theta. Once again, it is 90 degrees, so sine will turn into cos, and sine 90 degree minus theta, so sine 90 degree minus theta, all positive, so sine will turn into cos. But we need this theta in front because we are in place of theta we have omega t. Sine 90 degree minus omega t equal to cos omega t. We need this omega t in front now, because we will be comparing in such terms that E equal to E naught sine omega t and I equal to I naught sine omega t minus pi by 2 or plus pi by 2. In that we will compare it is ahead by 90 degree or behind by 90 degree. So we need this omega t in front. So what we do to bring this omega t in front, we take minus common. It's simple. If we take minus common, it will become minus 90 degree plus omega t, isn't it? And if we are taking minus common, this omega t minus 90 degree we can write like this, and minus whole minus outside, which will be equal to cos omega t, isn't it? This is pretty much clear. See, sine 90 degree minus omega, if we are taking common, minus will change into plus and plus will change into minus. It means omega t minus 90 degree, and this we brought minus outside. It means cos omega t means sine omega t minus 90 degree. So we write here minus sine omega t minus 90 degree. Minus minus will become plus. So E naught L omega sine omega t minus 90 degree. So we got the value of I to be this. I equal to E naught by L omega sine omega t minus 90 degree. Now you can say it is in terms of sine omega t minus 90 degree. It means we can convert, because E is also in such form, E equal to E equal to E naught sine omega t. So we can compare now. But remember, E naught is there, E naught is there. Sine omega t minus 90 degree, sine omega t is there. But what about the L omega? And one more thing, we need I naught here to compare, because E equal to E naught, it means I equal to I naught should be there. So again I said you that we use V equal to IR formula in the entire chapter here. So I equal to V by R. In place of V we write E, so I equal to E by R. It means I equal to E by R. So this L omega is playing the role of R, which is the resistance. Here we call it as the reactance. It is for inductor, so it is known as inductive reactance. So see, E equal to E naught by this L omega will play the role of inductance, which is denoted by X, and it is for inductor, so XL, it is denoted by X and in subscript L. So sine omega t minus 90 degree, and this is basically, this is resistance, so E by R means I, and it is E naught, so it will be I naught. I equal to I naught sine omega t minus 90 degree. In this way we get the two values, E equal to E naught sine omega t, I equal to I naught sine omega t minus 90 degree. And we can see that it is omega t and it is omega t minus 90 degree. It means I is lagging behind by 90 degree. It is lagging behind by a phase of pi by 2 or 90 degree. Or conversely, we can say that this voltage, it means EMF, it leads the current, alternating current, by a phase angle of 90 degree or pi by 2. So once again I'm telling you, these topics, the purely inductive, purely capacitive and purely reactive, they are not gonna ask usually. It's very rare question. Still, I told you the way how to calculate it. Once again, see, E equal to L di by dt. You need to remember the first step for each and every. Now E means E naught sin omega t. In this we got di, and then we just integrated it to get the capital I, and we just converted cos in terms of sine, because we need to compare it, so it must be in the similar terms. So since it needs to be in similar terms, we convert cos in sine, and omega t should be front, so we use minus. And how it came, I told you, using the Cos Rule. So finally it came I equal to E naught L omega sin omega t minus 90 degree. We need I naught here, so for I naught it should be E naught by R, isn't it? For I naught it should be E naught by R. So this L omega, which is in place of R, it is playing the role of reactance, resistance, which is known as inductive reactance, denoted by XL. So basically XL means inductive reactance, which is equal to omega L. And what will be its SI unit? Its SI unit will be ohm, because we know the resistance has the SI unit as ohm, and since it is playing the role of resistance, it will also have the SI unit of ohm. So finally we calculated I and E. So now we are going for the phasor diagram of this AC through an inductance only. Though this question is not asked, still I'm going to tell you each and everything about this. So now what the phasor diagram tells you, I told you first of all we draw the axes. This is the x-axis and this is the y-axis. We do not need this still. So as I told you, what we are drawing first, the thing we have written first. So here we have written E equal to E naught sin omega t in the beginning, so we draw E first of all, and E will always be bigger than I told you this in the purely resistive circuit as well. So this is this is the maximum value E naught, and this whole is E. And as per the derivation, I is lagging behind by an angle of 90 degree. So since it is lagging behind, so it will be behind this, and by an angle of 90 degree. So it is lagging behind, and E is bigger than I, so I will be smaller, and this is 90 degree or pi by 2. Okay, so this is I naught. Basically if you see this angle, this whole angle is omega t, and this whole angle is omega t minus 90 degree. Because this is omega t, this whole is 90 degree, so this will be obviously omega t minus 90 degree. So this is the phasor diagram, pretty much simple. And now the waveforms. So for waveforms, once again we'll draw the E first of all, because we are writing E first here. This is the time axis, which is omega t. Write omega t here, okay, omega t, and here we write I or E, and this is the origin. So first of all we divide it into 6 sections, as I told you. So just divide it into 6 sections. 1, 2, 3. So first will be the pi by 2, 90 degree, and then it will be 180 degree pi, and then it will be 3 pi by 2, then we will have 2 pi, and then we will have 5 pi by 2, and then we will have 3 pi. So first of all we draw E as normal. So draw the E as normal one. Remember to draw it of the same amplitude. So this is E, and this is its maximum value, peak value E naught, and this is E. So now we need to draw I. We know that I is lagging behind by an angle of 90 degree. Since it is lagging behind, it will begin after 90 degree of E. we begin E from here, so we'll begin I after 90 degree of it. It means this is 90 degree, pi by 2 means 90 degree, we'll begin from here, and it is smaller than E, so we'll draw it smaller. Okay, the rest of the things will be similar, just draw it smaller. And in this way you can even join this here. So in this way, this is the value of E, and you can see this is the maximum value I naught, and this is I. It is lagging behind by an angle of 90 degree. So this is the waveform for the purely inductive circuit, and now we have the purely capacitive circuit. So now purely capacitive circuit, first of all we'll draw a circuit as we drew in each of them. This is the AC source, which will have an EMF of E equal to E naught sine omega t, and here the current will be passing. Will not draw the directions because it is AC circuit, its direction changes periodically. And here we have the capacitor. This is the symbol for a capacitor. Now what is the work of capacitor? Basically you must have learned in your previous classes that capacitor, it is a device which is used to store the charge. Now it will store charge as much as it is supplied by the voltage. So first of all we begin from E naught sine omega t, as we begin in all of the purely circuits, all of the pure circuits. So now as we did in resistive, as we did in inductive, we have one specific formula for capacitor. Now that formula will be Q equal to CE. How this formula came, I'll tell you the reason. So see, I told you that the capacitor, it stores charge. Now it stores charge, which is Q. It is directly proportional to the voltage which is applied to it. It means the more voltage will be applied to the capacitor, the more charge it will store. And in place of V, we write E in AC circuit, we know that. And now since it is directly proportional, we have a constant which is known as C. Now this constant is known as the capacitance. So in this way, Q equal to CE is the formula we get. If you forget this formula, you can just remember that Q, it is directly proportional to E, and then a constant will come which is C. So here we have the formula Q equal to CE. Now we know E equal to E naught sine omega t. So Q equal to C E naught sine omega t. Now how do we get I from here? We know that I means dq by dt. We know I means q by t, so I means dq by dt. So we can just differentiate this q in terms of dt. So see, once again, in the resistive we just used the Ohm's law, which was V equal to IR. We got E equal to IR, then E equal to E naught sine omega t. We simply got I. In inductive we used E equal to L di by dt, and then we got di, we integrated to get I. In this we are using Q equal to CE. So Q equal to C E naught sine omega t. Now how do we get I from Q? Our basic target is to get I, because we are comparing E and I. So to get I, we know that I equal to dq by dt. So we can just differentiate it with respect to t. And to get I, we do not need to integrate here, we need to differentiate here. So we differentiate it, differentiating with respect to t. So if we differentiate, it will be dq by dt, and all these terms will get differentiated, d by dt, c e naught sine omega t. So we know that dq by dt is I. Now we just keep the constant terms outside. C, capacitance, is a constant. E naught is a maximum value, and maximum value is always constant. So C E naught, and the differentiable term is this sine omega t. And we know the differentiation of sine omega t. First of all, see, two angles are there, omega t. Here only t is there, so we need to make the angles first of all same to differentiate. So for making the angles same, we just write d omega t, and we multiply d omega t, and this dt will come here. This is just the balancing part. You must have read in the differentiation, angles are not same. For the formula, we need to make the angles same. So for making angles same, we are just multiplying and dividing this d omega t, and dt as it is. So now see, the angles became same, and now we have the formula. The formula for this sine is cos so it will become cos omega t, and this d omega t by dt, see it is a product rule. We can use the product rule if you want. First of all, omega and dt by dt plus this t d omega by dt. Now one more thing, omega is a constant because it is an angle. It means it is angular velocity here, and here it is constant, so this term will become 0. So remaining term dt by dt means 1. So the formula will be c e naught cos omega t dot omega, because this is 1, and simply you can do omega is constant, so bring omega outside, no product rule to be used. So just rearranging the formula, I equal to omega c e naught cos omega t. Once again we are in that part where we need to convert this cos into sine. The similar problem we had here, we got cos omega t, but we need to convert it in terms of sine. So once again we use a formula, and here we'll use slightly different formula. Now I'll tell you why we are using the different formula here. It means we are using the Cos rule, but you will use the formula of plus. First of all, let's use it. We know we need to get cos omega t, so for cos omega t we can use sine, because sine will be, we are finally calculating in terms of sine, so we need to convert cos in terms of sine. So what we do to convert cos in terms of sine, we take 90 degree, because in 90 degree the ratios get changed. So 90 degree, and we use plus omega t, which is equal to cos omega t. Now why we are using plus omega t? According to Cos rule, this formula is correct, because see, this is 90 degree and 90 degree plus, and in here cast, here s, all positive, so sin 90 degree plus omega t is cos omega t. But we could have used this formula in this previous one, in the inductive. We could have used this plus in place of minus, and here we can use minus in place of plus. But why we are not doing so? There is a reason. You can see here minus is there. Okay, we need to remove this minus, and for removing this minus we did all these things, because in final formula we do not have a minus. In E equal to E naught sin omega t we do not have minus, so how can we have minus here? So if we do not use this formula, this minus 1 formula, we simply use this plus formula here, it will become sin 90 degree plus omega t, and then minus will also be there, minus will not go. So we use minus 1 formula, we use this formula, and we take minus common to make sin omega t minus 90 degree. So finally we have cos omega t, which is equal to minus sin omega t minus 90 degree. You can rewind the video if you didn't get this. So in this way we got minus in the final formula, and then minus minus it became plus, and here there is no minus. If we use that same formula here, again minus will come in this formula. I'll tell you, see, if we use the minus here in plus of in place of plus, if we use minus here, we need to convert omega t in, we need to bring this omega t in front. So for bringing this omega t in front, we take again minus common, omega t minus 90 degree. So finally we have a minus in the formula, and we do not need that minus, so we are not using this minus, we simply use plus. So you can write this in this way, sin omega t plus 90 degree equal to cos omega t. Hope you got this thing, and if you didn't get, you can comment. I'll tell you personally. So now cos omega t it got converted into sin omega t plus 90 degree. Now again we need I naught here. I told you the logic that we need I naught here because E naught is there. So how do we get I naught here? What we do to get I naught, for I naught we know that it should be E naught by R, isn't it? We have E naught, but now for R what we do, see, E naught by 1 by omega c. We can write this omega c as 1 by omega c. Now this 1 by omega c, it is acting the role of resistance, it is playing the role of resistance, which is known as reactance. Now here it is known as capacitive reactance, which is denoted by xc. So E naught by xc means I naught. So in this way I equal to I naught sin omega t plus 90 degree. This is the final formula we get. Once again, E naught by 1 by omega c. 1 by omega c, it is playing the role of resistance known as capacitive reactance denoted by XC. Now since it is playing the role of reactance, so E naught by R, E naught by this XC will be equal to I naught. So we get the final formula I equal to I naught sin omega t plus 90 degree. From the beginning we just did that Q equal to CE, Q equal to C E naught sin omega t. We differentiated to get I. You can even use a simple logic that if you want to get I from Q, what we can do, we know the formula I equal to dq by dt, so we'll just differentiate it. We just differentiated it and finally we got this. Here we can see that the I is ahead of E by a phase angle of 90 degree. In the purely inductive circuit we had it behind the E. This I was lagging behind E by a phase angle of 90 degree. Here it is ahead from E by a phase angle of 90 degree. So now we'll draw the phasor diagram. So phasor diagram is pretty much simple. This x-axis. First of all we draw E. This is E naught, and now it is ahead. So it is ahead, then we'll draw in this direction, which is 90 degree. It is ahead by 90 degree. So we draw smaller. Now in inductive we drew here because it was behind. Here we draw in this direction because it is ahead. This angle is omega t and this whole angle is omega t plus 90 degree. So this is the phasor diagram. Now the waveforms. Omega t, I or E, and now again we divide it into 6 sections. Now as I told you that we draw E first of all because we wrote E first of all, so just draw simply. This is maximum value E naught and this is E. Now we'll draw I. We know that I, it is leading the E by a phase angle of 90 degree. So in lagging condition we drew after pi by 2, but here we need to draw before pi by 2. So if you produce this in this side, you can see one more phase is there, and from here it will become before pi by 2 it will begin. In the lagging condition, in the inductive case, we knew that it is lagging behind the E by a phase angle of 90 degree. So first of all we drew E, and then after 90 degree we drew I, because it is lagging behind by 90 degree, but here it is leading from 90 degree. So since it is leading, we'll draw before that and we'll draw 90 degree before that. So if you produce this in this direction, even here a section is there and from here it will begin. So basically it is beginning from here, and now just remove this, and now it is going in this way. And remember to draw it smaller. See, it is smaller. Okay, even here draw it smaller. Not from here, from here. So this is our maximum value I naught and this is I. So in this way we draw the waveforms. Once again, see, in the lagging condition we draw after 90 degree, but in leading condition we draw from here, from behind, because it is leading. So it started before 90 degree, and before 90 degree it started. It means in the figure you can see that we'll draw from here. Now finally, after this video I'll provide you the figures of each and every waveforms, so it will be easier for you to understand. So this is about the purely capacitive circuit, and with this we end all the purely circuits. Now once again, these questions might not be asked in the examinations, but usually the important part is this phasor diagram and then this waveform. And for each and every purely circuit you just need to remember the beginning. Like for resistance, for purely resistive circuit we started from V equal to IR, it means E equal to IR. For inductive we begin from E equal to L di by dt, and for this capacitive we begin from Q equal to CE. So in this way we begin every, and finally we compare the E and I, and these questions are not gonna ask. Still, I just told you for your information. And now we move on for the combinations. So now we have the alternating current through an inductor and a resistor connected in series. It means Lcr series circuit. This question is more regularly asked than the previous ones, the pure circuits, CR circuit, Lcr series circuit and LCR series circuit. These questions are more frequently asked, and trust me, they are more easier than the previous ones. So here we begin from I. First of all, we draw the circuit. So see, it is connected in series, so the circuit will be somewhat like this. First of all, there will be an AC source which will provide E equal to E naught sine omega t EMF. So current will be passing, no arrows because it is an alternating current circuit. So first of all, LR means inductor and resistor. So inductor, we have the symbol this, and then even resistor is there. So this is the figure. This is inductor L, this is inductor of inductance L, and resistor of resistance R. Now the voltage which is applied to this inductor, it is VL, and the voltage which is applied to this resistor, it is VR. Since it is in series circuit, what happens is that the current remains the same, but the voltage across the two appliances, like in this inductor and this resistor, it will be different. The voltage across them is different, but the current is same. This is the specification of the series circuit. So the current here will be same in both of them, but the voltage will be different. Its resistance is R and its reactance is XL. The inductive reactance which is here is XL. Inductive reactance means basically resistance which is trying to oppose it. Obviously there will be some opposition, there will be some resistance in this inductor also, which is denoted by XL, and its inductance is L, its resistance is R. So now this is the figure, and we begin from I. As I said you, in combinations we begin from I. So I equal to I naught sine omega t. The current which is applied to the circuit is I equal to I naught sine omega t. Now since they are connected in series, the current through them is same, but the potential difference across each of them, it means this voltage across each of them will be different. The total voltage, the total is E, the total EMF which is applied is E by the source, but across them it will split into two parts. So basically E will be equal to VL plus VR. The total is the same, but it gets split into two parts. So E equal to VL plus VR. Now it is basically a vector quantity, so we denote it in vector notation. So E equal to VL plus VR. After writing this much, we draw the phasor diagram to see which one is ahead, E or I. After drawing the phasor diagram, we'll know here which one will be ahead, E or I. So it is very simple. The things we need to do here are not complex. So the phasor diagram, we draw the axis. First of all, I tell you, draw whatever you have written first of all. So we draw here E, which is smaller, I naught. Now here is a trick. For the phasor diagram of combinations, wherever you draw I, just extend it to draw the VR. Always, in each and every combination, just extend the I to draw the VR. Okay, this is a trick, you need to remember this thing. There is no alternative for this, no logic. Just draw VR wherever you draw I. Now we know that the another one is VR. So now among VL and VR, which one is ahead? See, VR we drew, but now we need to draw the VL. Should we draw this side or this side? Which one will be ahead? So for that, here is a trick. You do not need to write this trick anywhere in the derivation. Just you need to remember this so that you do not get confused. We are drawing Lcr series circuit. So write the basic formulas for both the circuits. For inductor and for resistor, do this in rough. So for inductor, if you see, we know that E equal to E naught sine omega t. This is for pure cases. Okay, for pure cases, if you remember, E equal to E naught sine omega t for both of them. Here I equal to I naught sine omega t. For this it was I equal to this is I equal to I naught sine omega t for resistor, but for inductor I equal to I naught sine omega t minus 90 degree. we had for inductor as minus 90 degree. These were the formulas we got. Okay, but now in this Lcr series circuit you can see that I is same, so let's make I same and compare E. So for making I same, because I is same in Lcr series circuit, if we want to make I same, then if it is minus 90 degree, this I is now what is the meaning of this? That I is lagging behind E. We can also write that E is leading from I, so if we can write here plus 90 degree and remove this. Okay, the meaning will be same. The meaning is that this I is lagging behind E by 90 degree. We can also write that this E is leading by 90 degree, so the meaning is same. Now now the I became same. Now see, we compare the E, which one is ahead? Inductor is ahead. Here E equal to E naught sin omega t, here E equal to E naught sin omega t plus 90 degree. It is ahead, so we draw inductor ahead. It means in this direction. So we draw VL here. It means the voltage which is applied to the inductor. Voltage means this E. Okay, so we compare E and then we draw, and it is ahead by an angle 90 degree. It is sin omega t, sin omega t plus 90 degree. So it is ahead by an angle of 90 degree. This is 90 degree. This is VL. Now for E, this E will always be in between of this. Okay, you can draw anywhere, you can draw here, you can draw here, anywhere, but in between of VL and VR. These are the tricks I'm telling you, and you need to draw it bigger than I. So this is E naught. So basically we see that finally we come to this is angle omega t, and this is the angle omega t plus 90 degree. So finally we came to know that this E is ahead of I. Now how? Once again I'm telling you from the beginning. First of all, draw I wherever you want in this quadrant and just extend the I to make VR. Now we need to draw VL also, but where do we draw the VL? Ahead or behind? So for that we compare the pure cases. We compare pure cases by making I same. If we make I same here, it is minus 90 degree, it will become plus 90 degree in E. So now see E and E. This is omega t, this is omega t plus 90 degree. Resistor is just omega t, inductor is omega t plus 90 degree. So we draw omega t plus 90 degree. This is omega t plus 90 degree. So we drew VL here. V and E are same, so we drew it here. And now wherever you draw VL and VR, in between them we need to draw E. Wherever you can draw, but in between VL and VR will be E. Okay, so this is a trick. Wherever you draw I, extend VR, and wherever you draw VL and VR, you draw E in between them. So finally if you see the figure, you can see that E is here and I is here and E is here. So which one is ahead? E is ahead. So now we came to know that E is ahead by an angle theta, let's assume. But what is this angle theta? We're gonna calculate it now. So till now in writing part we just wrote this much: E equal to I naught sin omega t, E equal to VL plus VR, and then we drew the Phasor diagram. And now what you need to do is you need to remember that you need to use the parallelogram law of vector addition. Now in this combination there is no particular logic in using all these things, you just need to remember these things. Okay, so by using parallelogram law of vector addition, you can see E equal to, because you use the parallelogram law of vector addition here. Okay, it is vector quantity, so we use vector addition. If you use vector addition, we have the formula a square plus 2ab cos theta plus b square, isn't it? So VL square plus VR square plus 2 dot VL dot VR cos, we use cos pi by 2. The angle is pi by 2 used here because see the angle between VL and VR is 90 degree. Okay, so the angle between them is 90 degree, cos 90 degree. It means pi by 2. It is according to the formula. If you remember the formula, it is that R will be equal to P square plus Q square plus 2PQ cos theta, where theta is the angle between P and Q. So the angle between VL and VR is 90 degree here. So now obviously this is 0, so this whole term will be 0. So E equal to VL square plus VR square. We know that VL means what? I told you in the beginning that we use V equal to IR, this formula in the entire chapter. So V equal to IR, so we write for inductance, for the inductor it will be I into XL, because the resistance of this inductor is XL, and for resistance it will be normal IR square. Why we didn't write R here, we wrote XL? Because the resistance of the inductor, it is denoted by reactance, which is inductive reactance. I discussed this previously. So I common, first of all, I square XL square plus I square R square. So just take the I common, I square XL square plus R square. Now squares cancel, so E equal to I root under XL square plus R square. Now you can see this is in the form of V equal to IR again. Yes, again V equal to IR. It is in the form of V equal to IR. It means E equal to IR. So this E is there, I is there, but this R, this root under XL square plus R square, it is playing the role of R. It means it is playing the role of resistance, but here it is known as impedance, and it is denoted by Z. So Z equal to root under XL square plus R square, which is the impedance of this Lcr series circuit. So till now we calculated impedance. This was the formula to calculate the impedance. Now basically we need to calculate this angle now. This angle, what is the angle between E and I? For now, let us see from the beginning what we did. We just did I equal to I naught sin omega t, E equal to VL plus VR. Then we did the phasor diagram to know which one is ahead, VL or VR, and E or I, which one is ahead. So we came to know that VL is ahead of VR and E is ahead of I. Now what is the impedance of this Lcr series circuit, total resistance of this Lcr series circuit? We calculated the total resistance by using parallelogram law of vector addition. We used parallelogram law of vector addition. We used V means IXL, V means IR, and in this way E equal to I root under XL square plus R square. It means this root under XL square plus R square, which is in place of R, is playing the role of resistance known as impedance. So we came to know the total resistance of the Lcr series circuit, but still the angle between E and I is remaining. So now what is the angle between E and I? We assumed it to be theta. So we calculate it by using the parallelogram, vector rule, tan theta equal to VL by VR. This is the rule in which tan theta will be equal to P by Q. P means the bigger value, which is ahead. Okay, you must have read this in vector. So tan theta equal to VL by VR, because VL is ahead. So VL by VR. Now tan theta equal to, we know VL equal to IXL. Once again same thing, we converted VL into IXL. So XL and VR means IR, I gets cancelled. Tan theta equal to XL by R, so theta equal to tan inverse XL by R. So finally we came to know that, we know that E is ahead. E is ahead by an angle of theta. We came to know this from the phasor diagram, that E is ahead by an angle theta. It means omega t. If this current is I equal to I naught sin omega t, then E will be ahead by an angle E naught sin omega t plus theta. This theta, as we assumed, we came to know E is ahead, so plus theta. Now what is that theta? What is the theta? It is tan inverse XL by R. It means finally we come to know that the alternating EMF, it leads the alternating current by a phase angle of theta equal to tan inverse XL by R. That's all we need to do here. So once again from the beginning you just need to remember the steps. So if you see stepwise, what we do? First of all, the first step, we know I equal to I naught sin omega t. Second step, E equal to VL plus VR vectorically. Third step is the phasor diagram. Fourth step, parallelogram addition for impedance, and the final step is calculation of angle theta, okay, by using this formula. So these are the 5 steps you need to remember here, and it is very easy. This question is repeatedly asked. And finally we drew the phasor diagram, but the waveform is remaining. The waveform is also very simple here. The same thing, you just divide it into 6 sections. First of all, this is I or E, this is omega t. Now 6 sections. This is pi by 2, this is pi, this is 3 pi by 2, this is 2 pi, this is 5 pi by 2, and this is 3 pi. So now what we do first of all, what we wrote first of all, we draw that. Here we wrote I first of all, so we simply draw I. Sorry, it will be from here. So this is I, this is the maximum value I naught, and this is I. Now we need to draw E. So we come to know from this derivation that E is lagging behind. E is leading from this alternating current. So alternating EMF, it is leading by an angle theta. Now since it is leading by an angle theta, it means that it will begin before I, isn't it? The place from where I is beginning, it will begin before that, so it is leading. So now what we do is we just assume that it begin from this part. It just begin from here. Now do not begin it from an angle pi by 2 as we did in the capacitive. Okay, now you need to remember here one thing, that in capacitive it was leading by an angle of 90 degree, so we drew in this way, 90 degree in this way. But here it is just leading by a small angle of theta, which is tan inverse XL by R. Okay, it's just leading by a small angle theta, which is tan inverse XL by R. So though it is leading, but it is leading with a small angle theta, so it just begins from here. If it is beginning from here, if I is beginning from here, E will begin from here. Okay, because it is leading, so it will begin before that. So it is beginning and it will be bigger, as I said you, E is always bigger. So in this way you keep on drawing, this distance will be same everywhere. Okay, so this is it, and this difference between them is theta. This difference between them, everywhere this distance between them, you can see it is theta. Okay, and always E will be bigger. So this is the phasor diagram. You need to remember these slight details. Okay, otherwise it can go wrong. This is E naught, which is bigger than I naught, and it is leading by an angle theta. So that was about the Lcr series circuit. Now we go for the Cr series circuit. It is also very similar to this. So again, for the Cr series circuit, first of all we draw the circuit. E equal to E naught sine omega t. So first of all capacitor and then resistor, because it is Cr series circuit. I will be there. This is capacitor having capacitance C and R. Once again the current will be same, but the voltage across them will be different. Because it is series circuit. So this is VC, this is VR. The voltage across each of them will be different. Here it will have some amount of resistance which is known as reactance, denoted by XC. It will have R. Okay, so now first of all we write I equal to I naught sine omega t. As I said you, it is similar to Lcr series circuit. Again the E gets splitted up into VC plus VR vectorically we write. Then we do the phasor diagram, so we'll draw the phasor diagram. A phasor diagram is also pretty much simple, pretty much the same thing. First of all, as I said you, draw I. So this is I naught, and wherever you draw I told you to draw VR by extending it. So this is VR. Now we need to know where is VC, ahead or behind. So for that again we compare the pure cases. So write purely resistive and purely capacitive. You can do this in rough. So for purely resistive, what were the formulas? E equal to E naught sine omega t, I equal to I naught sine omega t. And for this E equal to E naught sine omega t and I. Now capacitive, it was leading, if you remember, the current was leading by an angle of 90 degree. So once again we need to make the current same. So for making the current same, we just write here minus 90 degree and remove this plus 90 degree. The meaning will be the same. The meaning is that current is leading by 90 degree and EMF is lagging by 90 degree. So the same meaning, EMF is lagging by 90 degree. If current is leading by 90 degree, EMF will be lagging by 90 degree. So now the current is same, I equal to I naught sin omega t, I equal to I naught sin omega t. Now compare the voltages. E equal to E naught sin omega t, E equal to E naught sin omega t minus 90 degree. It means capacitive is lagging from this resistive. So minus 90 degree, it means that we'll draw in this direction. In the LR series circuit it was plus 90 degrees, so we drew in this direction. In this it is minus 90 degrees, so in this direction. In this way we come to know where to draw VC or where to draw VL. It is lagging by 90 degree. And I told you, draw E always in between of VR and VC, whatever, VR and VL or VC, anything. Draw in between, anywhere in between you can draw. Let us draw here, okay. So this is E naught. Now you can see that I is ahead, E naught is behind. You can draw E naught anywhere, still E naught will be behind I. So in this way we come to know which one is ahead by Phasor diagram. So if this angle is omega t, this angle is omega t minus 90 degree, and the angle between I and E, let us assume to be theta, very similar to LR series circuit. Now we need to calculate the impedance of this whole circuit and then the theta, the impedance of the whole circuit, okay, by parallelogram law of vector addition, and then calculation of the theta, the fourth and the fifth step. So now parallelogram law of vector addition. By parallelogram law of vector addition, E equal to, just I'm doing it directly, VC square plus VR square plus 2 VC dot VR dot cos pi by 2. Pi by 2 means 90 degree. Why 90 degree? Because the angle between VR and VC is 90 degree. Okay, so again this whole term will be 0 because cos 90 degree is 0. So remaining VC square plus VR square. Convert VC and VR in terms of IR or IXC. Just use the formula as we did in the LR series circuit. VC means IXC. Usually V means IR, and here in capacitive the role of R is played by XC, plus for resistive it is normal, whole square both of them. I'm doing directly, I square will be common, so XC square plus R square will be remaining, I square will come outside, so root under XC square plus R square. Once again very similar to the LR series circuit, just in place of XL here XC is there. So this root under XC plus R square, XC square plus R square, it is playing the role of resistance once again, because it is in the place of R. If you see the formula E equal to IR, in place of R this thing is there. So this whole thing, it is playing the role of resistance once again. It is also known as impedance, as it was known as LR series circuit. So it is also denoted by Z, known as impedance. So Z equal to root under XC square plus R square. We came to know the entire impedance of the circuit. Now the final step, which is the calculation of the theta, angle between the I and E. So once again very simple, tan theta equal to VC by VR. If there is VC, use VC. If there is VL, use VL. Okay, it's very simple. You need to remember this thing, tan theta equal to VC by VR or VL by VR, anything. So VC means IXC, once again VR means IR, same thing, we just converted. It means we just used the formula, normal formula, V equal to I, which we will be using in the entire topic once again. So I cancel, XC by R. So theta equal to tan inverse XC by R. So this is the angle by which the E, it is lagging behind from I. We came to know it is lagging behind by an angle theta. So if I is I naught sin omega t, so E will be E naught sin omega t minus theta, because see from the figure we came to know that it is lagging. So it is lagging by an angle, what we assume the angle to be theta, but what is exactly that angle? That angle is tan inverse XC by R. So that's all about the CR series circuit. The remaining thing is only the waveform. So now see the waveform. Most of the things are very much similar in LR series circuit and the CR series circuit. Only in place of XL there will be XC, and in place of minus somewhere it is plus. So that's all we need to take care of. Dividing it into 6 sections. So this is 90 degree, this is 180 degree, and now here it is 3 pi by 2, 2 pi, 5 pi by 2, 3 pi. And one more thing, if you do not remember this, just remember in this way. First of all, write 90 and then 180. Okay, so see, pi by 2, then here it is 1. Okay, this is 1 pi by 2. So 1 2 3 and then 4 5. In this way you can remember. This is basically the same thing. 1 2 3 4 5. This is basically this 2 pi by 2, but 2 pi by 2 means 2 cancel pi, and then 3 pi by 2, and then 4 pi by 2, but 4 pi by 2 means 4 and 2 cancel 2, so 2 pi is there. Basically this is the same thing. Pi by 2, 2 pi by 2, 3 pi by 2, 4 pi by 2, 5 pi by 2, 6 pi by 2, increasing by 90 degree each. So first of all we draw I, because we wrote I first. So this is the maximum value I naught, and this is I. Now here E is lagging by an angle of theta, small angle theta. It is lagging. What is the meaning of lagging? That it is beginning after I. Leading means it is beginning before I. Lagging means it is beginning after I. First I starts and then E starts. Okay, and in leading condition, first E starts then I starts, as we did in Lcr series circuit. But in this Cr series circuit, first I starts and then E starts, because it is lagging by an angle theta. So after I, E will start. So I started here, it began here. After I, E will start. After how much after how much distance? Theta distance it will start. Okay, in the Lcr series circuit it began behind by an angle theta. It begin in this way, from this behind. But in this Cr series circuit, after I, so it is beginning here, and E is always bigger, so make it bigger. The rest of the things will be similar. Just to try to maintain the constant distance between them. So this constant distance is known as theta, this constant distance is known as theta, it is known as theta, and this maximum value is of E naught, that is the waveform. With this we complete Lr in Cr series circuit. Among Lr and Cr series circuits, this Lr series circuit is more frequently asked, so practice that much often. And then we have the final one now, Lcr series circuit. It is also similar to Lr and Cr series circuit, and that is the most repeatedly asked and most important question. So now Lcr series circuit is also very simple. It's not complex, but slight difference is there. You'll come to know the difference, but it is very simple, and this question is the most important question, so remember to pay full attention to this topic. So basically it is a combination, so it will be similar of Lr series circuit and Cr series circuit. The process will be similar from that. So first of all we make the circuit diagram. This is the AC source, which will provide E naught sine omega t EMF. The direction of the current is not shown because it is alternating circuit. So now Lcr series circuit means first of all inductance L, then capacitor C, then resistance R. Now it is series circuit, so since it is series circuit, the current is same but the voltage will be different. So voltage across this inductor will be VL. This is the middle part, so voltage for capacitor will be VC, and voltage for resistor will be VR. It is an impedance of reactance of XL. It has a reactance of XC, and its resistance is R. This is Lcr series circuit, the circuit diagram. Now we begin from I, because it is a combination, so I equal to I naught sine omega t. So the similar thing here, it gets split into three parts. This E will get split into VL plus VC plus VR. Now the similar thing, the phasor diagram will be drawn. Now here the difference will become what I was talking about. This is the phasor diagram, Y, X, X dash, Y dash, and O. So the same thing, you draw I wherever you want first of all, okay, and we just extend the I to make VR, as I told you. So VR is this is I. Now where to draw VL and where to draw VC, we came to know from the previous topics. we drew in Lr series circuit and Cr series circuit. In Lr series circuit, we came to know that VL will always be ahead of VR by angle 90 degree by doing all these things. In Cr series circuit, we came to know that VC will be behind the VR by doing all these things. So basically, we know now where to draw VL, and VC will draw VL here, which is 90 degree ahead of VR, and this is behind VR. This is VC, which is 90 degree behind VR. Now you need to remember that behind doesn't mean that its value is bigger. Okay, the value can be bigger of VL and VC, any of them. It doesn't mean that if VL is ahead then its value will be bigger. It is just that in the phasor diagram it is ahead. Okay, so if this is the angle omega t, this will be omega t plus 90 degree, this will be omega t minus 90 degree. Now where to draw E? Now that's the difference I was talking about. We can draw E here, we can draw E here, anywhere, but there will be only one E. So where to draw E? Now that depends upon the value of VL and VC. Whoever's value will be bigger, if VL will be bigger, then the E will be between VL and VR. If the value of VC is bigger, then the E will be between VR and VC. So how do we come to know whose value is bigger? We are doing a derivation, so all we can do is we can assume. So let's assume that the value of VL is bigger. Okay, so if the value of VL is bigger than the value of VC, so the net value will be VL minus VC, isn't it? VL minus VC. The net value of VL will be VL minus VC. For example, the value of VL is, for example, 5 ohm, and the value of VC is, for example, 3 ohm. So net value which will be acting upon between VR and VR and this VL, it will be 5 minus 3 equal to 2 ohm, because it is in this direction, but this VC is in this direction, so it will oppose VL. So finally the final value will be VL minus VC. So the final value will be VL minus VC, which will be acting. So the E will be between VL minus VC and VR. So you can draw wherever. Let's draw here, but remember that this E is not between VL and VR, it is between VR and VL minus VC. So now when we use vector addition, the parallelogram law of vector addition, even the difference will come here, because see, by using the parallelogram law of vector addition, we'll come to know about the total impedance which is acting in this Lcr series circuit. But remember that whenever you use parallelogram law of vector addition, we use for the things between which E is there. For example, in Lr series circuit, we were using the parallelogram law of vector addition between the VL and VR, because E was in between VL and VR. In Cr series circuit, we were using between VC and VR, because E was between VC and VR. So here we'll use for what? We'll use for VR and VL minus VC, because E is between VR and VL minus VC. So the first thing, VL minus VC square plus VR square plus 2 VL minus VC dot VR dot cos. The angle is same, 90 degree. They are separated by an angle of 90 degree. So just in place of VL or VC, we are using VL minus VC. So finally, VL minus VC square plus VR square, because whole this term will be 0, cos 90 degree is 0. So just go ahead with the basic mathematics. Just convert this VL into IXL, as we were doing in Lr series circuit and Cr series circuit. VL means IXL, VC means IXC square, plus VR means IR square. This XC and XL are also basically resistance R, but in case of inductance and capacitance, we use XL and XC. It means reactance. Till now you must have been clear about this. So E equal to, now just the basic mathematics here. I will be common, so I is common, and XL minus XC square. Okay, this is also square common, plus I square r square. I just took the I common here, okay. Before doing this whole formula, I just took this I common, okay. This is not square, this whole formula is squared, okay. I just took I common, I'm xl minus xc, and this whole formula is square. So if you see, it will become e I square xl minus xc square plus I square r square root under. So now again we can take common, so I common, I square we can take common actually, xc square plus r square will be remaining. Now I will come outside, I root under xl minus xc whole square plus r square. Once you can see this part, till here you must have got. So VL minus VC whole square plus VR square. VL means IXL, VC means IXC, VR means IR. So first of all, I took I common. So when we take I common, XL minus XC will be remaining. This whole is in square, okay. This whole is in square, and this I square R square as it is. Now again I square and XL minus XC square, okay. This I took I common. Now I just did square of both of them, I square xl minus xc whole square plus I square r square. Again I square can be took common, so I square common, and finally I came out. So here as we did in LR series circuit and CR series circuit, in this LCR series circuit, this whole part, it is in the place of R, so it is acting the role of resistance, and here it is known as impedance as well, as it was in LR series circuit and CR series circuit, which is denoted by Z. So Z equal to XL minus XC whole square plus R square. So this is the entire impedance, this is the impedance of the total LCR series circuit. Finally we calculate the angle by which E and I are separated. So as I told you, we assume the angle to be theta. From this figure, okay, remember I'll tell you about this more, but from this figure we come to know that E is ahead of I. For only this figure E is ahead of I because VL is bigger than VC as we assumed. So if we assume VL to be bigger than VC, E will be ahead of I by an angle theta to be assumed. So if we assume the angle theta, so we can calculate it by tan theta equal to, I told you VR will always be down and another one will be up. So what is another one here? VL minus VC. VL minus VC. So VL minus VC means IXL minus IXC by IR. I common, IXL minus XC by IR. I cancel, XL minus XC by R. So finally theta equal to tan inverse XL minus XC by R. So for this case, the case in which inductance is leading the capacitance, it means VL is leading the VC. For this case, E will be ahead of I by an angle theta, and that theta is XL minus XC by R. But now see, here is the controversy. What if the VL and VC is same? Okay, so there are three cases. First of all, what we did from the beginning, same thing as we did in LR and CR series circuit. Circuit diagram split it into three phasor diagram. From phasor diagram, we came to know E is ahead of I according to this figure because VL is bigger than VC. Then we do the parallelogram law of vector addition for the impedance, and finally we calculate theta by using tan theta. So these 5 steps we did, and now there are 3 cases. For first case, we just assumed VL to be VC. What if the VL and VC are equal? So if VL and VC are equal, then you can see that this theta will be, if VL and VC are equal, XL and XC will also be equal. It's obvious that if VL and VC are equal, it means XL and XC are equal. So if they are equal, this XL and XC means XL minus XC will be 0 because they are equal. So tan inverse 0, where all this value will be 0. So tan theta will be 0. So for this case, E will be equal to E naught sine omega t. See how? If VL and VC are equal, it means XL and XC are equal. For this case, this formula tan inverse XL minus XC by R, what we calculated, this whole will be 0 because XL and XC is equal. So this theta will be 0. So this E equal to E naught sine omega t, as we calculated here, that it is leading by an angle theta. So this theta is 0. So if theta is 0, E equal to E naught sin omega t. So E equal to E naught sin omega t. In this case, LCR series circuit, it is purely behaving as purely resistive circuit, because see, I equal to I naught sin omega t, E equal to E naught sin omega t. Same thing, it is behaving as purely resistive circuit. Now the second case, the case that we assumed, it means VL is bigger than VC. The case that we assumed, if VL is bigger than VC, it means XL is bigger than XC. For this case, this formula will be applied. This formula will be positive because XL is bigger than XC. So this formula is positive. So basically the value will be as we assumed, omega t plus theta. So in this case, you can see it is behaving as an inductive circuit. Okay. In this case, it is behaving as inductive circuit because the EMF, it is ahead of current, and this was the case of inductive circuit. So it is behaving as inductive circuit. Now the third case, what if the VC is bigger than VL? So if VC is bigger than VL, it means XC is bigger than XL. Then this whole formula will become negative. It means XC is bigger, so this formula will become negative, to be obvious. And if this formula becomes negative, the formula will be transformed omega t minus theta. Because theta will be negative, this theta will come in negative, and so in place of plus there will be minus. So in this case, it will behave as capacitive circuit. So these are the three cases that can happen in this LCR series circuit. So basically LCR series circuit can behave as purely resistive circuit, as an inductive circuit, and as a resistive circuit as well, as a capacitive circuit as well. So this is the specifications of the LCR series circuit. There is no waveform in this, and with this we end LCR series circuit. It's very simple. The only difference is that there are three different cases which can happen here. Okay, still we use this second case for our derivation. It means that VL will be bigger than VC. We use that for our derivation. I'll give you each and every derivation after the end of this video, and each and every figure. So with this we end all types of combinations of the circuits. To be remembered, LCR series circuit is most asked, and the other ones, the purely inductive, purely capacitive, and purely resistive, they are rarely asked. Almost it will not be asked. LR and CR series circuit is to be practiced properly, and the formulas need to be remembered for each and every circuit, because it is very important to remember the formula of purely inductive, purely capacitive, and purely resistive for these combinations as well. Now these things, if you see combinations, they are so easy that you can just mug it up. I know it's not a nice way to mug it up, but they're so easy, you can really mug it up. This you need to do is that the Phasor diagram, the parallelogram, law of vector addition, and finally you need to do this calculation of the theta by using tan theta. And till now you must have remembered that VL will always be here, so and VC will always be here. So the things can be mugged up pretty easily. And that's all for this video. In the next video we'll be discussing about the power of the alternating current. Till then, take care, goodbye.